Thank you, Nathan. Thank you all for showing up today, and I'd like to thank ESI for the hospitality. I feel very lucky to be here. So that's my abstract I put up there. So you all have been reading it, so this is what I'm going to be covering in today's talk. So some comments, for hundreds of years, and this is probably one of the best places to make these type of comments, is for hundreds of years, people like Laplace and everybody and all the 20th century mathematicians, physicists made comments. Give me the equations, give me the initial conditions, and I'll tell you what's going on forever. Well, we learned after, starting in the late part of the 19th century and definitely going into the 20th century and to present day, that's not quite true. Poincare's nonlinear dynamics told us it's not true. Now, in the mid-20th century, there's a very large development where a number of very well-known scientists like Van Neumann, Stanislav Ulam, etc., started looking at deterministic problems and solving them statistically via like Monte-Carlo methods. And then at the same time, or slightly before that, quantum mechanics came on board, which shook up the physics community, brought the stochastic nature into problems that seemed deterministic, and it's very, fitting at the Schrödinger Institute. I think the same thing is starting to happen in oceanography, where last century, everything was deterministic, and now things are becoming much more stochastic. So to do ocean modeling, and here we're talking about numerical simulations of ocean circulation, what do we need? We have to assume some dynamics. Navier-Stokes equations, potential vorticity equations, maybe QZ dynamics, quasi-geostrophic, dynamical equations, shallow water equations, simplified. We have to assume some set of dynamics, take a domain geometry, bottom topography. And of course, mathematically, there's no answers until we impose boundary conditions, some initial conditions. We need to know forcing, dissipation operators, which is very easy on a molecular scale, becomes much more difficult at a finite scale, and then numerical methods and computational resources. And traditionally, once you made these choices and started your simulation, everything was deterministic. First of all, I want to show you some pictures of the ocean bottom. We'll start off nice here. I'll show you some beautiful pictures. These were done with a very expensive side scanning sonar from one of my colleagues, Gregor Eberle. And you see the scale bar down there is 2 kilometers. These are very small features, and these are off the Florida coast. Here's some more, examples of these features. And really, when you look at the topographic databases that are out there, most of these features are not in those topographic databases. Now, when we get closer to shore, we have structure like this, very large structures all over the place. These are the coral reefs off the coast of Florida, what they used to look like. That's a whole lecture in itself. And if we look at ocean topography, let me see if I can adjust the placement of this slide. It seems like as I going through here, we're losing something. I don't know how I'm going to be able to do this. All right, not that important right now. We got two examples. Here, this is what the bathymetry in many models look like. To the left, in the middle is what we're making measurements now. We predict what the bathymetry is, but when we really go in and look at high resolution surveys, special surveys like the data I just showed you, it looks like more of the pictures on the right. So we're missing a lot of structure and resolution in our topographic databases, which is important. Now also, in atmospheric models, this is what they assume the coastline looks like, right? Now, if you go down to my neck of the woods, what does the coastline look like? It looks like this, 50-story buildings. I do a lot of fishing out there. It's one of the reasons I left Harvard, went down to Florida, and I stayed. The fishing is good, the weather's good. The wind blows through these buildings. You know how much shear it sets up? When you're in a boat, you can see it because the wind gets amplified going through the openings and it's blocked by the buildings. So it sets up a whole series of fast, slow slopes, wind, fast and slow along the coast. That's a lot of shear, small scale, that's going into the real world ocean that's not incorporated in our textbook oceans. All right, so let's talk about forcing. What do we need from ocean models in general? We need wind stress, we need evaporation, precipitation, freshwater flux, terms. We need all of the heat flux terms. Now, when we look at these forcing data sets, we could have a perfect model, perfect initial conditions and boundary conditions, but if we bring in the present day forcing, after a while, our model doesn't look like reality because the forcing is missing a lot of the high resolution, high wave number, high frequency component of the signals because of the coarse space-time sampling of our instruments, which gets further compounded by the fact that these data sets are collected irregularly in space and time and then are interpolated by objective analysis and similar methods, which further smooth these fields. So we're forcing our models with a field that's deficient. Now, people like Mike Chin and his colleagues decided they wanted to do something about it. And here's one example where they took a European Center wind reanalysis. They took the scatterometer, which has a lot of high resolution data, a long track, but of course a resolution cross track. And they figured out, they did some wavelet fitting, looked at the coefficients, calculated the statistics of the coefficient. And from that, they were able to generate a stochastic component where they projected the high frequency, high wave number information, a long track over the domain, and then put it together with the reanalysis. And it produces a wind field that energetically is more like the real world than any of the reanalysis products. People are starting to look at adding stochastic elements to forcing, and one of the results that people see, it does energize the ocean. We see more rigorous mesoscale. Sordo and Yang said it improved their model output by looking at verification data by including a stochastic forcing term into the equations. Now, mathematically, the deterministic Navier-Stokes equations can be derived from a stochastic Navier-Stokes equation. One way to go from deterministic to stochastic is to add a stochastic forcing elements. And, you know, there's a lot of theory behind this, but the thing I want to point out is the last line in one of these papers, as I quote, finally, let us point out that numerical methods tied up with our probabilistic approach still have to be developed. So they were able to prove some nice mathematical results where, for example, in the stochastic Navier-Stokes, they were able to look at some simple flow situations and show, at least in the weak solution sense, there are unique solutions, which is a big thing to the Navier-Stokes. If you could do the strong solution over the whole time and stuff, you can, you win $1 million, right? The Millennium Prize, if you could do that problem. And, if somebody asked me about forcing with respect to ocean model, what would be my recommendation? It's simple. We need more and better forcing data. Stochastic models could help, but things will only get much better with much better data sets. And luckily, the Europeans, us, everybody's putting satellites up to help with this. So it's really obvious that dynamics, geometry, and forcing are important. So what about initial conditions? How important are they? Now, if we have a really strongly forced nonlinear flow, they only really care about the initial conditions for a few integral timescales. After a while, the system forgets about the initial conditions in this flow configuration. Now, when you look at ocean flow, we don't fall in that regime, but we have ways to correct bad initial conditions in our ocean models. And how is that? Through data assimilation. We could assimilate data to correct our bad initial conditions and also to keep our nonlinear models on track. So let me just show you some quick results that was done a little while ago with twin experiments. We were in the Miami isopycnal coordinate ocean model, which became HICOM, the hybrid coordinate ocean model, which is used for operational prediction by NOAA and the US Navy. So we did a classic double gyre, subtropical gyre, polar gyre, where you blow sinusoidal winds over the ocean to create a circulation. And what we're going to do is sample this ocean with altimeter data and run an altimeter track over it. And we're going to do twin experiments. And in the twin experiments, we have a truth run. And from that truth run, we're going to pick a really bad initial condition. And we're going to do data assimilation on it. And then we're going to do no assimilation. And what happens is the no assimilation case takes forever to try to forget about those initial conditions. But data assimilation, on the order of a few months, things start getting corrected. So first of all, here's the altimeter sampling pattern for our domain. Day 1, that's where we get the tracks in our domain. Day 2, and all the way up to day 10, we show you the tracks we get on day 10, and the tracks in the light color are the tracks we got over the previous 9 days. So this is the 10-day repeat pattern that Nathan was talking about earlier today, and this is the tracks. Very high resolution data along the tracks, less than 10 kilometers, or 6 to 8 kilometers, but very coarse resolution between the tracks. So we're going to do this in a MICOM model, 100 by 100 grid, 20 kilometer grid resolution. So showing you how bad we're starting. So this is the truth field for the day that we want to do the twin experiment for. And on the top panel is the prediction at day 0. So we're taking a field that is really different, not just a little different, it's really different. So, this is a hard test. We could have, did an easier test. So this is a hard day, a harder test. So after 30 days of assimilating data, we get fields that are starting to look a lot more similar. And then by day 100, 6 months, it catches up. So let's look at the error statistics. And so we have the error statistics, RMS error on the left-hand side. And then we have the errors in the velocity on the bottom 2 panels. Note, we're only assimilating sea surface height. The velocities are updated through the dynamical model. And so we see a very sharp decrease in error on the timescales of 2 to 3 days. And the other thing this shows is if we update every 20 minutes to about every 2 days, we get less error than just throwing all the data in every 10 days. Here's a plot that shows a little bit of those differences. So on the top is where we did 10-day updates. We only put the data in through the simulation every 10 days. On the bottom, 2 days. And if you look hard, you can see that the flow on the bottom, particularly if you look at this eddy versus that eddy, it's a much stronger flow. So the initial conditions ain't a problem for us because we have data assimilation and data being collected. Now, the other thing people are doing is ensemble forecasting. They use multiple initial conditions to generate multiple predictions. I showed a hurricane example here. I live in Florida. We care a lot about hurricane trajectory. So here's showing 2 different simulations of hurricane paths using a Monte-Carlo approach, where they go in there and they perturb the initial conditions with known error and run the model. Well, here's the problem with Monte-Carlo methods. You produce all this output, and then you have to average it together. So here is 3 realizations from a toy case. And if you take those 3 realizations and average them together on a fixed grid, a fixed Eulerian average, so at every grid point, you just average the variables, we get the picture on the bottom. And you can see that the picture on the bottom really doesn't look like these other 3. Now, if we do a contour-based analysis, we could get a picture that will look like up number 2. And if you're interested about contour analysis, I talk about it in a couple of papers. The first one was in 1990. And basically with the contour analysis is we pick contours and we average the position of contours. Now, in a more general case, where we're producing, say, temperature maps, and we have, 200 temperature maps produced by ensembles that we want to average together. If we do the averaging of those ensembles on a fixed grid, we're going to smear out the magnitude of our temperature changes and the gradients in temperature. So for there, my recommendation is you find the maximum temperature, you set that as a local 0, 0 on a polar coordinate system, and then do the contour-based averaging, and you get away with you reduce all of this smearing problem associated with ensemble averaging. So ensemble, doing Monte-Carlo simulations is good, but in our field, they're not averaging the results right, unfortunately. So here's another example of averaging stuff, and here we'll just do 2 realizations to keep it simple. These are 2 model simulations of oil patches off the coast of Louisiana, United States. This was, of course, related to our big oil spill in 2010. And shown here are 5 different averages of putting those 2 patches together. So let me remind you, here's the patches. If I did an Eulerian average and try to average, in a fixed grid, you get a mess. It looks terrible. I don't even want to show it. It looks bad. It's not science, it's wallpaper. Now, depending on what feature we key in on, we get slightly different maps. So in the upper left-hand corner, where I'm pointing to is the feature that we're keying in. On the right, another feature. Here we're keying in on this part of the flow. And then on the lower, your right, we're keying on another feature. And then in the middle, I consider my best algorithm where I used 4 points to do the averaging. And I get an average that makes sense, that looks good. It has all of the predominant features in the data set that's available. All right, so let's talk a little bit about boundary conditions in our models. They determine the solution. You know, people like Norman Dershowitz told us all that. Classic boundary conditions and models of free slip, no slip, and then some mixed free slip and no slip. To remind you, free slip assumes 0 tangential slip. It's not like the boundary's there. The boundary's not, it doesn't feel the boundary. On the other extreme is no slip, where this is based on molecular ideas that the flow is exactly 0 at the boundary. But if we're solving an ocean simulation on a fixed grid, 10 kilometers by 10 kilometers, 20 kilometers by 20 kilometers, wherever your resolution is, the boundary condition is going to contain contributions from unresolved fluid. And that unresolved fluid can have significant energy at small scale. So here's an example from high frequency radar measurements of the surface velocity field off of Fort Lauderdale, Florida. And the peak flow there is over 1 meter a second, and there's a lot of small scale structure. Now, if I have a 20-kilometer horizontal resolution, this box is about 10 kilometers by 10 kilometers, this flow wouldn't be represented at all in that box as part of the boundary condition, but you can see there's a lot of significant motion. I had a video, but we're having problems and it didn't run, but the video shows you that in this domain, a whole bunch of eddies go streaming through here, and these eddies have radiuses less than 5 kilometers. So this is significant nonlinear vortices going through your domain, and you're not representing them at all using classical boundary conditions. So a number of years ago, 20 years ago, where does the time go, right? We had this idea of stochastic boundary conditions. So we started with a simple quasi-geostrophic model. So you need to know stream function, you need to know vorticity, and we assumed a very simple stochastic boundary condition. So at the lower part of the domain, we're going to generate stochastic noise using different stochastic models, like a Markov model, autoregressive model of order 1 and higher order models. And then we're going to take that signal and we're going to propagate it along the coast. And by equation 3, the propagation is very simple. We're going to move it with a dominant phase speed that we believe is important for that region. So here's a space-time order correlation calculated from that velocity data set. We have lag in hours on the bottom, and then the vertical axis is kilometers. And if we take the slope of that, that's the displacement velocities. And here it was on the order of 60 centimeters a second, which is for the ocean is pretty fast. So how well does a stochastic model represent the motion? So here's an arbitrary pick. So on the top, you could tell is the real data. It's a little bit noisier. And on the bottom is our very simple stochastic model. So it's not exact, but it has the qualitative features. We're only, calculating one stochastic model over the entire time, over the domain. So, it was good enough to try for the experiments. It looks a bit like the real world. And then we could try to do other stochastic models. So this is a power spectral density function as a function of cycles per hour. Power, of course, is on the vertical axis. And we show you for some different models. So the light gray line here is the actual data set. A TW model, as you can guess, it has equal energy at all the frequencies as a white noise model, Brownian type of motion. And then here we have a T0, and the T0 model is picked to hit the peak in the power spectral density function right there in the middle. That peak is associated with 12 hours. in this particular area. It's kind of an odd number, but it's related to the very large shear in this region. The shear there is, the Rossby number is order 10 to 12 at times, an average of 4 to 5. So it's a very nonlinear, strongly sheared system. And then we have model T1 that models the low frequency, and then model T2 that models the high frequency really well. So there's different stochastic models we could apply, and then in the research game is try to decide which one does the best. So QG model, very simple. We did a few different, geometries in this. I'm going to assume that you're all familiar with QG modeling, but it's a local change potential vorticity, nonlinear advection, the beta term, and we're using a biharmonic operator for friction, and we have some Ekman forcing. So here's snapshots of the transport in there. So on your left is the free slip in panel A. Panel B is no slip. So in the free slip, you could see it doesn't really feel the boundary much. And this is periodic. So whatever goes in one end comes out, whatever goes out one end comes in the other. It's just for simplicity. So the no slip shows a regular train of eddies being formed of pretty much the same size. And here's two different realizations from our stochastic simulations showing eddies of different sizes, not as regular, and a much more energetic ocean. The Hofmöller diagram, again. So here we have longitude, west to east direction, and time running up to 6 years. So we put like 30 Sverdovs of flow originally into this problem, uniformly distributed over the boundary. On the time scale of the Rossby waves crossing the boundary, we get a western boundary current. So that's why everything starts getting very small. This is due to western boundary dynamics. And what we see here is the free slip, no slip in the stochastic. So it gives us a much different solution with a much broader band phenomena being existed, i.e. there's more energy and more frequencies in the stochastic solution than in the no slip or the free slip case. And these eddies penetrate further into the interior. So this was a simple periodic channel. So we did some other simulations where we put a cape in there. And here we have 6 different stochastic realizations, and these are the mean stream functions. So free slip really doesn't know too much about the cape, just a little bit. No slip. The upper right is a white noise case. And with the white noise, if you think about it, the dissipation operator is going to destroy that uncorrelated space-time variability that you're adding in pretty quick. So the white noise and the no slip are fairly similar. And then on the bottom, we have T0. T1 is the low frequency. T2 is the high frequency. And you can see, depending on what stochastic model we use, we generate much different flow patterns with this. And then if you look at the kinetic energy in terms of mean and eddy kinetic energy, the important takeaway is when you look at the eddy kinetic energy for the stochastic model, T1, it's much more energetic than the classic boundary conditions out to very large values of the viscosity. And this is a result we've seen in all of our simulations, this type of result. We did the classic double gyre, and shown here is the mean stream function for 4 cases: free slip, no slip, the white noise case, which again looks somewhat similar to the free slip condition, and then the T1 condition. And the thing to point out with T1 is our jet penetrates much further into the interior, and it's a much more energetic jet. And shown here are the zonal speeds for the different simulations as a function of distance offshore. And we could see that the T1 case produces the much more energetic flow regime. I'm not going to go into the details of this table, but the separation statistics of the stream are also different. So we believe that stochastic boundary conditions can help us really energize our models at a very low cost. All right, so now let's get to what to do about friction or dissipation operators. If we go through the history of it, the simple Rayleigh friction, the friction is proportional to the velocity. Stommel used that in his model of the the Gulf Stream circulation, the analytic theory. And then a lot of people use the classic eddy diffusivity, where we take the molecular form of a Laplacian and we just crank the coefficient up 8 orders of magnitude and things like that. And that's a second order operator. Now, other people have used higher order operators, fourth, sixth, etc. Greg Holloway had an interesting idea saying, well, when you think about the friction, the Laplacian is operating on V, and really that's relative to an equilibrium solution of no motion. He argued maybe that operator should be working on V minus the geostrophic solution, which was a lot easier to do with simple analytic problems, but becomes more difficult to do with a full-blown numerical simulation. And then the latest and greatest dissipation operator is based on the ideas of Gent and McWilliams. And their idea was, let's parameterize the effects of the eddies on the flow. And think of baroclinic instability. And what does baroclinic instability does? It flattens the isopycnals, releases available potential energy into eddy kinetic energy. And so it's, based on the eddy-induced transport. It depends on layer thicknesses. It depends on the velocity gradients like these other operators do. And then Janssen and his colleagues in a series of papers took the McWilliams, added a biharmonic oscillator, and then a negative Laplacian. And now the negative Laplacian operator, what does that do? It allows the reverse cascade of energy, which is a predominant feature of two-dimensional turbulence. It basically allows energy backscatter, which we see, again, in two-dimensional turbulence. You don't see it in three-dimensional turbulence. And one could argue, is the ocean 2 or 3? And everybody says, well, it's 2.5. And if you don't want to give it a number, let's call it geostrophic turbulence after Rhines and Leith and people like that. Now, another approach for a dissipation operator is, let's not even think about physics. Let's do signal processing. What do you want your operator to do? We want to remove 1 to 2 point grid scale noise. So there's a Shapiro filter that does a really good job of removing 1 to 2 point noise and leaving the energy at the other scales basically untouched. So here's one example from Eric Chassamet. Eric Chassamet did this run. Actually, he did this with Zuluma Grafo earlier than this 2008 paper with Marshall, but these figures were, came out a little bit better than the conference proceeding of the original. And so here on your left, we're using a biharmonic viscosity operator, fourth order. And on the right, we're using a second order operator. And you can see the Gulf Stream separation is much different. So it really does make a big difference what operator you use. And this is one result. This result is seen by many people. And Greg Holloway mentioned eddy diffusivity can be a dangerous concept, for these operators. All right. Let's explain this figure. And I love this figure. My students are sick of seeing this figure. All right, so these are SOFAR floats in the main thermocline. At each point where you have a position of the float, we're going to put a point, and then we're going to form triangles by matching up the floats closest together. So you hit one float here, and then you find the two closest, and you make a triangle. And then after you look at this a whole bunch of times, you go back and color code it. So in the lighter gray is a wave. It turns out to be a Rossby wave that was observed and discussed by Tom Rossby and Jim Price. And the interesting thing about it is, Rossby waves, the theory, C.G. Rossby, came up with them in the late 30s. His son, Tom Rossby, was the first one to really measure one by throwing floats in the ocean. That's kind of cool. And then the really dark shading has to do with an eddy. So let's look at the wave, and the white shading is the background flow. So let's look at the wave as this panel moves in time every 7 or so days. When you look at the wave, if you look at the first panel and the last panel with this wave, there's not mixing going on. There's no mixing. You look at the eddy, on the other hand, there's a lot of mixing going on, and mixes the background flow with it. Well, here's the interesting thing about all of this. If you look at the velocity gradients associated over these fields, all these velocity gradients are the same order of magnitude. But all our classical dissipation operators, they depend on gradients and Laplacians. But the mixing is very different. It depends whether you're in a wave or you're in an eddy. So if we're doing these calculations on our Eulerian grid, yeah, it makes, and you want to have some idea with the classic physics and things like that, you got operators that depend on the local gradients. But that's not in the ocean, it's not the story. Here's a simple one counterexample that shows you if you just base stuff on gradients to your mixing and your dissipation, you're going to be in trouble because it's feature dependent. It depends on the feature you're in. All right. Let's talk about Neptune rolling dice for dissipation. Let's talk about stochastic dissipation operators instead of classic dissipation operators. First question you might want to ask yourself, why do you want to look at stochastic dissipation for ocean circulation models? Well, first thing I say is why not? We have a lot of unresolved scales in our numerical models, topography, and all, initial condition boundary for effort. We have unresolved scales in everything. You look at Reynolds decomposition, where you're trying to solve for the mean flow, and if you could think in a model, when you do the calculation over a grid point, it's really the mean flow over that space-time volume that depends on the model resolution. And the Reynolds decomposition is a stochastic statement in itself. As I mentioned a few moments ago, adding a stochastic noise term have yielded some unique weak solutions to the Navier-Stokes equations in very special cases. A review is given in this reference. And people have started using stochastic dissipation operators in very simple flow problems. And here's a list of references. But again, these are simple flow problems to show that stochastic dissipation operators is a good idea. Some of these algorithms look at the energetics and allow an inverse cascade backscatter of energy, just like Jansen's study where he included a negative Laplacian. And the thing, though, in most of these papers, they looked at high resolution numerical simulations to get the statistics to set what the operator should look like in low resolution models. Or the other thing they did is they assumed some easy spectra based on, say, QG theory, for example. The spectral slope is k to the minus 5/3 or minus k to the minus 3. You pick some spectra based on some simple theory. And the reason there was a lot of stuff with high resolution into low resolution is how to parameterize these eddies in low resolution models that are part of the coupled climate system. You can't put every model very high resolution in a coupled system. So everybody's looking at how to parameterize the eddies in the lower resolution models. And the other reason we should do it's time. Berner et al. With a whole list of very well-known authors, a few years ago in the atmospheric sciences says stochastic parameterization is the new view of weather and climate models. And I believe it should be the new view also for ocean models. All right, so here from John, we were lucky enough to have John for physical oceanography, John Canals, and showing you that what helps determine the evolution of the mean flows is the divergence of the Reynolds stress terms like U prime, V prime bar, and its divergence. And that's a stochastic statement, U prime, V prime bar. That's what's going to affect a mean quantity at a point. So let me give you some ideas for a stochastic differential operator. You're all young, you could do this stuff. I'm done. I don't have time to do this, but some ideas. So you generate different model ensembles using stochastic boundary conditions or different initial conditions. And I would suggest using a Shapiro filter for these. Calculate the mean model state from the ensembles, being very careful about what I said about how you do the averaging. Because if you just take everything on a fixed grid and averaging, it's not going to work. Use the mean state to calculate the residual velocity fields that you can then use to calculate the Reynolds decomposition. So then the question is, how do you do the space-time averaging? Do we do it in a model run in some space-time volume in the area of interest? Or we're getting to a point with computational power is, do we take all these models, running it in a parallel mode, and do the averaging over all the ensembles? That's doable now. And some last thoughts on all of this. Can we use the power spectral density function of velocity calculating extremely high resolution fluid flow? Can we use these in ocean models by using Eulerian stochastic models. We would perturb our velocity fields, the U and V fields. We would perturb those from the model output at a given time using these Eulerian stochastic models, and then do that a lot, and then average over those results the divergence of the Reynolds stress terms. But what I think the real future is, and I hate to say it because I'm not a big fan of AI, is basically AI is, what's the big use of AI is going to be? It's to drain our wallets. That's what it's going to be. Artificial intelligence. I mean, that's what a lot of people, dynamic pricing is the buzzword. Everything's going to be dynamic pricing based on demand, and it's to get the last dollar out of you. But in the sciences, AI is making some progress. But I think the real good use of AI here is that it should be used to pick out features in your model simulations. And once you pick the features out, have a stochastic dissipation operator that is based on the features, not Eulerian velocity gradients, for example. So this might be, I think, the best use of AI in the ocean and in the modeling is to do feature-based dissipation. We're not going to do it next year, but I think that's the future. Thank you. Are there any questions?